Hello. Hello. Okay. All right. Let's get started. So in our last lecture, we So in our last lecture, we discussed what is deep generative models, okay? Or generative models. Okay? So generative models in mathematics, they are essentially distributions, right? So when we say we develop generative models over data, basically we are defining the distributions over the data. And given the generative models, we can use them to generate data. Right? Basically, we can perform data generation. And in math, data generation basically is sampling, right? Drawing samples from the distribution. Each sample you draw from this distribution would be a new data generated. So starting from this lecture, we are going to talk about how do we define these generative models, or how do we define these distributions. So we also mentioned that so the generative models or graphical models So throughout the lecture, we are going to use the terminology generative models or probabilistic graphical models. They are basically the same thing, right? So we are going to utilize two mathematical tools. One is the probability theory. The other is the graph theory. In your previous probability or statistic class, right, you guys dealt with a lot of different distributions. Right? In those cases, the distributions are relatively simple. You can basically write down their density function. Right? For example, if you want to work on a distribution of real numbers, you utilize a Gaussian distribution defined. So x is the random variable. Mu is the mean, and the sigma square is the variance. Right? You can write down the density function, which is 1 over 2 pi sigma square root exponential function, then minus 1 over 2 x minus mu squared. Right? So you can write down the density function. Then you can basically do the algebra calculation, etc., to deal with this distribution. However, when you are defining the distributions over very complex data like images, texts, or tables, etc., you cannot use a simple distribution like this, right, to model the data. Right? It is too simple to model the complex data. So we are going to need need tools that can allow us to define these distributions effectively. So the tool we are going to use is a graph. Let's see what's the process of using a graph to define a distribution. So if you define a distribution using the graph, then you basically get a generative model or a probabilistic graphical model. Okay, for the next step, let's talk about how to use a graph to define a distribution. Can you guys see this part? Okay, all right. Let's maybe use an example to illustrate the process. Suppose we want to work on an application basically determining, right, or asking what will be my letter grade in this class, right? Suppose I'm taking this class, what would be my letter grade that I can get after the end of this quarter? Yeah, so the application is determine the grade determine my grade in this class. So the first step we need to do is to identify all the key entities, key concepts relevant to this application. Identify, let's use objects, right? Objects to identify objects relevant to the application. So what do I mean by objects? Basically, it's any concepts or some entities that are relevant to this question here, right? So one object obviously is the grade, right? My grade, ABCD, right? So the grade can take value either A or B or C or D. So what things determine my grade in this course? One thing I can think of is the difficulty of this class, right? Difficulty level. For simplicity, let's just assume that the difficulty is a binary variable. It is either 1 or 0. So if the value of this variable is 1, it means this course is difficult, right? If it's 0, it means this course is easy. Certainly, the difficulty determines my grade, right? If the course is difficult, then probably my grade is going to be low, right? If it's easy, probably my grade is going to be high, right? Another thing is maybe it is my let's say my learning capability, learning ability. Let's also assume it is a binary variable, either 1 or 0. If it is 1, it means I have very good learning capabilities. And if it is 0, means I'm not very good at learning. Right, so if I am good at learning, then probably I will get a good grade. Otherwise, I will probably get a lower grade. Yeah, so these are basically, we call it objects, right? Basically some concepts that are involved in this application, right? Okay, now we identify these objects. So after identify these objects, we are going to put them into a graph, right? So basically, we treat each concept object here as a node in a graph. Right? So in a graph, you have the nodes, and the nodes are connected by edges. Right? So after we identify these objects, we can put them on the nodes of a graph. So this is the first step. Right? So after this step, the next thing we need to do is to identify the relations between objects. So now let's look at these objects and see whether they are related. So one relation is the difficulty of this course determines my grade, right? So we draw a edge from difficulty to grade. So there is a direction here. This direction basically means this guy here is causing this guy, or this one is dependent on this one, right? So because difficulty determines grade, then we have a edge connecting difficulty to grade, and the direction is from difficulty to grade, right? So we basically use a directed edge to denote this choral effect. Another thing, another relation is the learning ability also determines my grade, right? So we connect this node to this one in this direction, right? Again, because grade is dependent on my learning capability, or in other words, my learning capability determines my grade. So we have a directed connection from this guy to this guy. Then for difficulty and learning capability, they are not related, right? They are totally independent things. So there is no connection between them. By doing this, we have the entire graph, right? We put these objects on the nodes, and then we connect these nodes based on their relations. Right? After doing this, we get a graph, which is a directed graph, right? Since the edges here are directed. Okay, so the next step is maybe I can write it here. Okay, the next step is we are going to utilize this graph to define the distributions over all these variables. So this part, the first part, is about graph design, right? We first design this graph. So this graph basically encodes our domain knowledge about this application, including the objects and the relations. After we have this graph, the next step is to define the distribution. Okay, so under distribution define, we have 3 steps. The first step is to assign random variables to nodes. Okay, so we have 3 nodes here. What we are going to do in this step is that we are going to assign a random variable to each of them. So for difficulty, let's use a variable xd to denote the difficulty. And for learning capability, let's use xl to denote the learning capability. And for the grade, let's use xg to denote the learning capability, to denote the grade. The intuition of using random variables to model these objects is because all these things have some randomness, right? For my grade, right, there might be some probability that I will get A, right? Some probability that I'm going to get B. So I basically have, there is some possibility that I can get any of this grade, right? It's not something deterministic. For sure, I'm going to get A after this course, right? Yeah, so the chance that I'm getting A or B or C or D is all random, right? So we use random variables to model the grade. Similarly, for the learning capability and for the difficulty, there are also randomness, right? It's not something deterministic. Yeah, so we are going to use random variables to account for the randomness in the objects. Now let's look at these objects. For difficulty, it is a binary variable, right? For binary variable, what distribution do we use to model a binary variable? So in your probability class, did you guys learn probabilities over binary variables? So there is a distribution called the Bernoulli distribution. Bernoulli distribution. Yeah, Bernoulli distribution is basically defined over binary variables. In our next lecture, we are going to do an overview of probabilities and statistics. Right? So if you guys are not familiar with these distributions, do not worry. We are going to give an overview in our next lecture. The Bernoulli distribution, it defines the probability is something like this. So P defined over this variable xd. So this probability equals to P if xd equals to 1. And the probability is 1 minus P, let's use a different parameter, 1 minus, let's say, gamma. 1 minus gamma if xd is 0. Right, so gamma here is the parameter of this distribution. It is a number between 0 and 1. So if the random variable, the value is 1, the probability is R. If it is 0, the probability is 1 minus R. Yeah, so this is basically called a Bernoulli distribution. Then for L, the learning capability, it is also a binary variable, right? We can again utilize a Bernoulli distribution to model it. And the parameter, let's say for this variable, pxl equals to, let's use another parameter because it is a different distribution. Let's say it is lambda, right? So the probability pxl equals to lambda if this variable xl equals to 1, and the probability equals to 1 minus lambda if the variable is 0. So they are both Bernoulli distributions, but since they are utilized to model different probability, different objects, so their parameters are different. So gamma and lambda are different. Okay, now let's look at this grade. So the grade is, it takes 4 values, A, B, C, D. And all these values are discrete. And in this case, we use a distribution which is called a multinomial distribution. Multinomial distribution to model variables like this, right? So for variables that are taking discrete values, we utilize multinomial distributions to do the modeling. So a multinomial distribution is an extension of Bernoulli distribution. Right? In the Bernoulli distribution, it is a binary variable. You have 2 choices, either 1 or 0. And in the multinomial distribution, you have multiple choices. Right? You have here we have 4 choices, A, B, C, D. Right? So a multinomial distribution looks something like this. The probability that xg equals to A is, let's say it's alpha 1. The probability that xg equals to B, it is alpha 2. The probability that xg equals to C is alpha 3. And then the probability that xg equals to D, it is 1 minus alpha 1 minus alpha 2 minus alpha 3. Right, so if you look at compare this distribution and this one, they are very similar, right? The only difference is here you have 2 variables, here you have 4 variables, right? So alpha 1, alpha 2, and alpha 3 are the parameters of this distribution. They are all numbers between 0 and 1. Okay, so after this step, we basically finished assignment of random variables to the nodes. And after doing this, we basically get a graph of random variables, right? X D X L and XG. Right, so we assign a random variable to each node here. Then you can put the random variable on the node, right? XD, XL, and XG. The edges remain the same, right? And after doing this, we get this graph of random variables. Where on the nodes, we have the random variables, and they are connected using edges. Okay, any questions so far? Yeah. Mm. Yeah. So it's just like example. We here for simplicity, we assume it is binary. Yeah, as you mentioned, maybe a Gaussian, a continuous number is more proper. Right? So the choice of these random variables for these different objects is basically designed by you. Right? You can either if you believe the learning capability should be a continuous number, then you use a Gaussian distribution. If we believe it is a binary variable, we use Bernoulli distribution. Or we can even do something in the middle. Say, let's say for the learning capability, there are 3 levels, maybe L1, L2, and L3, right? And in that case, you can use a multinomial distribution to model it. So this is totally determined by your design, right? Any other questions? Okay, great. So after doing this, maybe I can just label this as numbers, so we do not get confused regarding. So let's say this is 1, this is 2. Right, in step 1 and 2, we design the graph. This is 3. So in step 3, we are defining the distribution. Okay, after the third step, we get a graph of random variables. Then in the fourth step, so fourth step is still about define the distribution. Define the distribution. Let me mark it as continued. Yeah, so step 3 and step 4 are both about defining the distribution. The fourth step is write down the joint distribution of all the variables. Okay, so given this graph of random variables, we can directly write down the joint distribution of all the 3 variables. It's an easy process. So the joint distribution of xd, xl, and xg equals. The procedure for writing down the joint distribution is like this. So we look at all these nodes one by one. Let's look at this guy first. So if the node is does not have parent, right? So basically here xd has no parent, xl has no parent, and xg has 2 parents, right? D and L are the parents of this guy. Right, so this is some concepts in graph theory, right? So in a directed graph, if there are connections from these 2 nodes to this one, then these 2 nodes are basically called the parents of this node, right? And for D and L, they have no parent because there are no directed connections connecting to them, right? Okay, so for a node, if it has no parent, we just write down the marginal probability xd, right, pxd, because it has no parent, right? So we just write down the probability pxd. And for this node, it has no parent either. Right? So the same thing, we just write down the marginal probability of this guy, Pxl. And then for this node, it has two parents. And in that case, we write down a conditional probability. The probability is defined over xg, but we condition on xd and xl. Because d and l are the parents of g, right? Okay, so you can see that from this graph to the joint distribution, it's a simple procedure. You basically look at every random variable in this graph. If the variable has no parents, you just write down the marginal probability at p directly defined over this variable. If the variable has parents, then you write down the conditional probability condition on the parents of this node. Yeah, that would, then you multiply them together. That would be the joint distribution. The joint distribution of the three variables. Yeah, to avoid confusing, let me use dot to denote the multiplication. Any questions in this step? Yeah. Yeah, so that's a great question. So so this is basically a Bayesian network. Yeah, a graph a directed graph defined over random variables. We call it a Bayesian network. Yeah, so for a Bayesian network, the joint distribution of all the variables defined in the network basically can be written in this form. There are some theorems proving that this one and this one, they are equivalent. They are called IMAPs. So in this course, due to the schedule limit, we probably cannot dive into the details of the proofs. If you guys are interested, right, you can read the textbook, the first textbook by Daphne Koller and Friedman. They have the detailed proofs regarding why this joint distribution can be written in this way. But yeah, in the lecture, we probably do not have time to cover it. Yeah, so from an application perspective, you just need to remember that after you define this Bayesian network, you can directly get the joint distribution using this formula. Right? That would be correct and complete. Yeah, so it's called IMAP. Right? You can check the textbook regarding the detailed proofs. Yeah. XL is a parent node. Oh, if it has a parent node, let's say if there is another variable, say x a, right? Then you have a different graph, right? Then for that case, then we have the joint distribution over 4 variables instead of 3. Right? We have an additional random variable xa, right? Then the joint distribution for these 4 random variables is the same procedure, right? So you write down pxd because d has no parent. Then for this new variable xa, it has no parent, so it's pxa, right? Then for xl, now it has a parent, so we need to write it as pxl condition on its parent, which is xa. Right? Then for xg, it's the same. It's its parents is xd and xl. Right? So the rules are the same. Yeah. So if the node has a parent, then you need to write down a conditional distribution. Okay. Any other questions? Okay. Yeah. So so for a directed graph of random variables, it is called a Bayesian network. And given a Bayesian network, just look at the graph structure, you can immediately get the joint distribution of all the random variables. Okay, so this is step 4. Then let's talk about step 5. Step 5 is specify the individual distributions in the joint distribution. Step 5 is still about define the distribution, right? Let me still mark it as continued. Yeah, so steps 3, 4, and 5 are all about defining the distributions. So step 1 and 2 are about design the graph. Okay, so yeah, after you write down this joint distribution here, it is a product of the individual distributions, right? Now we need to basically specify what these distributions are. I already did some here, right? So for pxd, because it is a binary variable, so we use a Bernoulli distribution to model xd. So pxd is basically just this guy, right? So pxd equals to gamma if xd equal to 1, and 1 minus gamma if xd equal to 0. We already discussed this there. So we get a pxd. Then for pxl, we also discussed that, right? It's also a Bernoulli distribution. So pxl equals lambda if xl equals to 1, and 1 minus lambda if xl equals to 0. Okay, we get these two. Now let's look at this one, right? So this one is a conditional distribution. It's a little bit more complicated. So pxg, right, condition on xd and xl. So xg is a multinomial variable, right? It can take the value a, b, c, d. It conditions on its parents, the value of its parents, right? So for xd and xl, we need to enumerate all the possible values for these two variables. So since they are binary, their values could be 0, 0, right? 0, 1, 1, 0, and 1, 1, right? So under each configuration, we need to define this probability over xg. Okay, so here for the parents of xg, we have 4 scenarios, right? 4 configurations. Under each configuration, we need to put down some probability for xg equals to A or B or C or D, right? So we can use some parameters. Let's say we use this notation. So alpha 0, 0. So I'm putting 0 and 0 on the superscript, meaning that it is under this configuration of its parents. Right, so it would be alpha 1, 0, 0. The probability that xg equals to A is alpha 1, 0, 0, when the value of the parents of xg is 0 and 0. Right, so here it's just a probability number between 0 and 1. Right? Then we can do the same. So alpha 2, 0, 0, and alpha 3, 0, 0. Then for D, it's basically 1 minus alpha 1 minus alpha 2 minus alpha 3, right? Then for xd and xl equals to 0 and 1, you can do the same thing, right? Put down some probabilities here, and then do the rest for the rest of rows. Okay, any questions? Yeah, so the definition here is similar to this guy here. The difference is previously we assume that G has no parents, right? So it's simply alpha 1, 2, 3, and 1 minus alpha 1, 2, 3. Now, when you are defining this distribution, because it is a conditional distribution now, you need to condition on the values of the parents. Right, so when xd and L equals to 0, 0, you need to define some probabilities. When it is 0, 1, you need to define some other probabilities. Right? Okay, any questions? Yeah, so after doing this, we basically finish the entire design of the model, right? And in the end, what you get is you have this graph, you have this joint distribution, and within the joint distribution, you define all these individual components. Right? For each component, you have the parameters, gamma, lambda, and also these alphas. Right? You have everything about this model. One thing we are missing here is we don't know the exact values yet. So what is the value of lambda? Right? We don't know yet. So how to learn the actual values of these parameters? We are going to defer this to the lecture when we talk about how to learn the parameters of the distribution using maximum likelihood, the EM algorithm, etc. But when we are designing the model, right, you just so when you get to here, then you are done, right? You don't need to know the values of the parameters. You just need to specify them, right? And the actual values will be learned in the next learning task. Right? So here, after you finish this, we basically finish the design of the model. Yeah, let's do a recap. So overall, we have 2 steps. One is to design a graph. The other is to define the distribution by leveraging the graph. When you are designing the graph, you need to identify the key objects that are needed in your application. And then you need to identify the relations between the objects. Right? Given the objects and the relations, you get a graph. Then in the next step, you assign random variables to the nodes. And then you write down the joint distribution. And then you define the individual distributions appeared in the joint distribution. Yeah, so after these 5 steps, you basically get a Bayesian network. Any questions? Okay, all right. So next, let's so following this procedure, let's see how a large language model is designed. Right, so large language model essentially is a Bayesian network. So let me walk you through the steps using these 5 steps to define a large language model. Let's take a 5 minutes break and come back in 5 minutes. Okay, now let's discuss how to follow these 5 steps to define a large language model. So a language model basically is a distribution over text, right? So a text, so in a text, for example, in a sentence, we have these individual words, right? For example, let's put it down a random sentence. So today, I like apple because it is I like apple because it is delicious. So we have a sentence like this. Now we want to build a distribution over this sentence, or a distribution over any sentence. Let's follow the 5 steps. Right? In the first step, we need to identify the key objects. So in this, in the language model case, the objects are simple, straightforward, right? It's basically these individual words, right, in the sentence, right? So we are modeling a sentence, and in the sentence, it is a sequence of words, right? Then we basically treat each word here as an object, right? So the objects here are straightforward. So we put each node, each word here as an object and put it onto a node. I like apple, etc. Right? Basically, for each word here in the sentence, you put it onto the node. The next step is to identify the relations. Identify the relations between these nodes. So let's say for this like, the second word, right? It depends on the first one, right? So when we are writing a sentence, we write it from left to right, right? We first write the first word, then after that, we write down the second word. And when we are writing down the second word, of course, we need to look at the first word to determine what we should write for the next word, right? So in that sense, like depends on I, right? Then for apple, it's the same thing. So after you write down the first 2 words, now you are going to write down the third word. And this third word depends on the previous 2 words. Right? Then for the rest, it's basically the same. Each time you write down a new word, you look at the words you already wrote, and based on the semantics and the grammar of the previous words, you determine what you write for the next one. To give you an example, let's say, suppose we already write, I like apple because it is. Now we are going to write down the next word. And for the next word, we have some choices. Let's say because it is okay. So we have three choices for the next word: delicious, easygoing, and smelly. So we are not going to choose the word easygoing, right? Because we are talking about apple here. We cannot use easygoing to describe apple, right? And also, we are not going to use the word smelly because we have this word like, right? I like something because it has some good aspects, right? Smelly is something bad, so it is not compatible with like. Right? So delicious is the best word because it can be utilized to describe apple, and also it is consistent with the word like, right? Yeah, so in this example, I'm trying to basically illustrate that when you are determining the next word, you basically look at the semantics and the grammar of the previous words to determine what should be the next word, right? So based on that intuition, this graph will be something like this. So for every word, there will be directed connections from the previous words to this current one. Right, based on the intuition we just described. So for a certain word, it is determined by all the previous words. Right, so there will be connections from each previous word to this current word. Right. Any questions about this part? Oh, sorry. Yeah, a single arrow. Yeah. Yeah. So because it has three previous words, yeah. So there are three arrows. Yeah. So this is a Bayesian network, right? It is a graph, and it is a directed graph. Okay. Then for the next step, okay, so for the next step, we are going to assign random variables to the nodes. So for each node here, representing a word, we are going to assign a random variable. Let's use W1, W2, W3 to denote these random variables for word 1, word 2, word 3, etc. And their connections remain the same. Right. So from W1 to W2, from W1 and W2 to W3, etc. Right? Okay, now let's look at this random variable. What kind of distribution we can choose to model a word. So a word is basically one of the choices among the entire dictionary, right? Among the entire vocabulary. Suppose in our vocabulary we have, let's say, 10,000 words, 10,000 unique words. This is our dictionary or vocabulary. Then for a particular word, such as apple, it is one of the 10,000 words, right? And in this case, it is discrete, right? All these words are discrete. And it is one of these many choices. And what kind of distribution we use? We basically use this multinomial distribution. Right? Here, you have 4 choices, A, B, C, D, in our previous example. And in the language model case, you have 10,000 choices. You are going to pick one of them. Right? So we can use basically the multinomial distribution to model this distribution. So yeah, we are going to use multinomial distribution. The distribution is basically similar, right? For each word W, there is some probability that if W is apple, the probability is, let's say, gamma 1. If it's another word like, the probability is gamma 2, etc. Right? You basically do this for all these 10,000 words. And for each word, you put down some probability. Yeah, that would be the parameters of this distribution. Right? So here it's the same as this distribution here, right? Just here you have 4 choices. There you have 10,000 choices. Okay, so we are done with the assignment of random variables. Any questions in this step? All right, the next step, we are going to write down the joint distribution. Okay, so this is the Bayesian network we have, right? It has such a structure. Then we just look at the structure and we can write down the joint distribution. So P, probability of W1, W2, let's say we have n words, Wn. So this is a sentence with n words. We look at each node in this graph, see whether it has parents or not. So for W1, the first word, it has no parents. So we just write P W1, right? Now let's look at W2. So for W2, it has a single parent, right? W2 is the second word. It has only one parent, which is the first word. So we basically write PW2 condition on PW1, right? Then for the third word, PW3, it has 2 parents, which are W1 and W2, right? W1 and W2. Right, you can do this. So in general, when you write PWK, right, for a certain word in the middle, WK, you are going to condition on W1, W2, W3 up to WK minus 1, right? So we use a notation 1 K minus 2 K minus 1 to denote W1, W2 up to WK minus 1, right? Yeah, so the notation is W1 K minus 1. So it basically denotes W1, W2, WK minus 1. So in English, what do you call this guy here? Comma? Colon. Oh, colon, I see. Yeah, so 1 colon K minus 1. So this notation basically denotes W1, 2, 3 up to WK minus 1. Yeah, you can do this, right? And the last one would be PWN. The parents would be W1 to N minus 1. Right, so this would be the joint distribution. Any questions in this step? Here we are just following the structure of this Bayesian network. Right. Any questions? Okay, now it's the last step, right? The fifth step. So in this joint distribution, we have these individual distributions. We need to determine what they are. So for the first token, PW1, it's simple, right? It's just this multinomial distribution, right? PW. Then you put down some parameters here for this multinomial distribution. Then for these guys, these conditional distributions, so what we do? If we look at this general form here, right? So how all these individual distributions take this general form, right? PWK condition on all the previous words, 1 to K minus 1, right? So for this distribution, if we can define it, then we can basically, we are done with all these guys, right? Because all these guys are taking this form. And for this one, it is so complicated, right? Imagine that now you are writing the 1000 and let's say suppose K now equals to 1001, right? Then its parents, it has 1000 parents, right? W1 to W1000, right? So how are you going to define a distribution that take 1000 words as input and generate a probability distribution over this word W1001? Right? How are you going to define it? Right? It's something complicated. So that's where the neural networks come in. Right? So what we can do is basically we define a neural network. Let's see. And by the way, the fifth step is defines individual distributions. Because this conditional distribution is so complicated, we are going to use a deep neural network to do it. So in general, this deep neural network, let's use a box to denote it. So deep neural network, the input would be the words W1 to K minus 1. Right, so it is a sequence of words. And the output would be a distribution over WK. Right, so just to reiterate, we want to define a distribution for this guy here, WK, condition on W1 to K minus 1. It is very complicated, so we are going to use a deep neural network to do it. The input to the deep neural network is the parents. So it's basically W1 to K minus 1. The output would be a distribution over WK, the current word. And this deep neural network should be flexible that it can take any, so for this key value here, it could be different, right? So for this guy here, W2 condition on W1, key equals to 2, right? And for this guy here, key equals to 3. And for this one here, key equals to n, right? Yeah, so basically, at different positions, right, we have these different conditional distributions. The length, the number of the previous words is different. So when we are designing this deep neural network, we should be able to deal with that varying number of input words, right? So then we can use a single deep neural network to define distributions for all these conditional distributions. We cannot say we define an individual neural network for each of them. Then you can imagine that you need to maintain like thousands of deep neural networks. That's not feasible, right? So we want to use a single neural network to define all these conditional distributions. Because for these different conditional distributions, the number of words in the parents are different. So this deep neural network should be able to deal with the input that has different number of words. Right? Okay, all right. So this is the high-level idea of defining this deep neural network. Now let's dive into the details regarding how to design this deep neural network. You guys learned, have you guys taken some deep learning classes? For this particular task, what do you think we can, what deep neural network we can utilize to do this? Yeah.
A transformer.
Yeah, a transformer, yeah. Any other choices? RNN, yeah. Any other thoughts? LSTM, Yeah, so basically, you guys are getting the point, right? We can use the recurrent neural network, LSTM, and the transformer, right? Basically to define this deep neural network. And so if you choose a transformer to be this deep neural network, then you basically get the state-of-the-art large language models. Yeah, so the language model is a pretty old thing. It was invented, I guess, 70 years ago. So previously, people, before neural network comes, right, people just use tables to define these distributions. So for this guy, PW2 condition on W1, you can basically design a table like this, right? So for W1, it can take these different values, right? And then condition on the value of W1, you define the probability over W2, right? So basically, PW2 condition on PW1, you can design a table similar to this to specify the probabilities. Then for PW3 condition on PW1 and PW2, you can design a bigger table to do it, right? For W1 and W2, you enumerate all these possible values, right? And under each configuration of W1 and W2, you specify the probabilities of W3. And then for PW4, it becomes harder, right? Because now you have 3 parents. 1, 2, and 3. Suppose you want to design a table to define this distribution, right? Imagine that how many rows you need to have. So for W1, it has 10,000 choices. And for W2, also another 10,000. For W3, another 10,000, right? You basically need to utilize 10,000 to the power of 3 to define this table, right? You have so many rows. And even worse, when you define, say, PW1000 condition on W12999, right? In that case, you basically need 10,000 to the power of 999 to define that table. Right? This is not feasible, right? And because of this limitation, they basically make an assumption that for any word, WK, it only depends on the previous word, WK minus 1. This is a simplified assumption to reduce the computational complexity. But we know that it doesn't make total sense, right? Because when you write a word, you need to look at all the previous words instead of just the previous single word, right? Yeah, so that's how people do language modeling before deep learning comes. And you can see that there is a lot of limitations, right? And now, that's why at that time, the idea of language model, they can do something, but not as powerful as ChatGPT that can help you to generate so realistic texts, right? Simply because the model is very limited because of these simplified assumptions. And then later, people basically introduce deep neural networks into this task, starting from RNN. Now the state of the art is transformer, right? We are going to talk about the transformer when we come to the specific lecture about large language models. Right? Here it's just we are using it as an example to illustrate how to design a Bayesian network. Later, we are going to talk about the more details about large language models, and we are going to introduce what is a transformer. Basically, to summarize, language model is an old idea. It becomes so powerful because transformer is utilized. And when transformer was utilized in the first version and the second version, GPT and GPT-2, it's not impressive at all. Actually, the generated text is very bad. Then researchers basically keep increasing the size of the model. And when the size of the model reaches a huge scale, suddenly something very magical happens. That is what we have for large language model nowadays. Okay, all right, I will see you guys next week.
我选了285，还有这门课，这我看 syllabus 感觉区别不是很大。
对，你就上285就行了。
但是我现在还没有选上，因为我之前选了那个王小龙老师那门课，然后但是就是我现在才了解到，我其实是可以选2个285。但是你觉得我现在就是但是我现在还在 ECE 上没有挂上。
那个我已经 approve 了啊。
对，就是我285那个还要被 department。就是如果
对你选那个就可以了。
选那个就可以。这就都差不多是。
总体来说差不多，这个可能就是更偏那个基础一些。比如说这里面涉及到那个 graphic model 的一些东西，我们可能不会在285